3D trig. Now 3D trig, by the way, is extension 1. Okay, so whilst the rest of the trig that we're doing was just review of basic trig, you won't see a 3D trig problem in a 2-unit paper. Now, 3D trig can often be hard to visualise what's going on because sometimes the diagrams sort of play visual tricks with you and so on. I often find it useful to redraw the different sides in 2 dimensions and then try and link the shapes together. It was quite a good question back in 2003. Yes, David's in a life raft. Anna gets the cabin cruiser. Yeah, that'll be right. Searching for him. He's lost. They're in contact by mobile phone. David tells Anna, who's changed the way she spells her name, that he can see Mount Hope. From David's position, the mountain has a bearing of 109, angle of elevation to the top of the mountain, 16 degrees. Fortunately, they had those measuring instruments with them, as you would when you're just lost on a raft. Okay, Anna, who now realises her mistake, can also see Mount Hope, and from her position, she also happens to have the instruments to measure, found its bearing of 139, top of the mountain, angle of elevation 23, and they also happen to know that Mount Hope is 1,500 metres above sea level. Find the distance and bearing of the life raft from Anna's position. I love maths in the real world. Okay, so here's the picture they gave with all that. There's the nice cabin cruiser and the raft. So basically I'm going to redraw some of these triangles in 2 dimensions. So we've got triangle HDB. We know the height's 1,500, angle of elevation 16. Then we've got the cabin cruiser. So there's another right angle triangle there. Then the third triangle, I guess, would be looking down. So the ground, well, the water, not the ground, the water, I guess. So here's David. We knew the bearing of the point B, which is the base of Mount Hope, was 109. But then Anna, she looked at it and her bearing was 139. So that creates another triangle. So we had to find a few things. Let's try and link these things all together. Now, we're trying to find, what were the 2 things we had to find? It was distance and bearing. So I've labelled that B, and the bearing would be the angle from north here that I've labelled theta. And we've got a triangle. At this stage, we don't have any sides and we don't have any angles, but we should be able to work some out. Using these triangles, okay, BD over 1,500 will be tan 74. So I know BD is 1,500 tan 74. Using the other triangle, I could do a similar thing and come up with AB is 1,500 tan 67. So, okay, I now have 2 sides of my triangle. If I have one angle, I should be able to use a cosine rule and come up with B. So we've got some 139 here. We know that's 109. Bit of geometry. We should be able to work this out. Going to draw another north in here at B, because what it basically does is create another parallel line, which allows us to use alternate angles, co-interior angles, those sorts of things. So if you're looking at that, we've got NDB, DB, what I labelled north with 2 dashes. That was the new one I drew in. They'd add up to 180. They're co-interior angles. So DBN 2 dashes ends up being 71 degrees. And I could do a similar thing and come up with ABN double dash as 41 degrees. And then angle sum of a triangle. Oh, no, common angle, sorry, not angle sum of a triangle, because ABD is made up of the other angles. And we get 30 degrees. 30 degrees ends up being. So we can pop that in. So now I have the perfect scenario where I've got 2 sides and an included angle. I should be able to find B via the cosine rule. All right, 1,500 squared, tan squared, etc., etc. B turns out to be, to the nearest metre, 2,799 metres. That was the first part. The bearing as well we wanted to find. Okay, so we know how far apart they are. Let's go back to our diagram. We want to find that green angle there. We know to the blue line's 139 degrees. We have now worked out that that's 30 degrees down there. That might be useful. We know that's 109. Let's see, how did I do it? I used a sine rule and found angle DAB. because we've now worked out what B is. And when I'm doing this, I don't use, of course, the 2799. That's just an approximation. I keep this exact value stored in my calculator so I can use that value. It may not make a difference, but sometimes the rounding error can cause problems. And we end up with, eventually, two possibilities because I'm using sine. So the question is it acute or is it obtuse? So it's either going to be 69.9 or 110.51. But if it turns out to be 69.9, angle BDA would then be 80 degrees 51 by angle sum of a triangle. But we know DAB has to be bigger than BDA. And that's because of the sides of the triangle. We know the biggest one is opposite the biggest angle and so on. So therefore it must end up being the obtuse angle. And I guess when they did this in the HSC, a lot of people would have made that mistake and assumed it was the acute angle. If you used the cosine rule for this, if it was possible to. You had enough info?
Yeah.
Yep, okay, so cosine rule would have solved that problem. All right, so we now know that angle is in fact obtuse. We should be able to work out the bearing then, because all we've got to do is add that onto the 139. And we get a bearing of 249, what does that say? 51. So just watch out for things like that. Don't always assume it's going to be acute when you're using the sine rule. Classic 3D problem where you've got a pyramid, if you like, or a surveyor. Now, well, a surveyor would have all the instruments to work out the angles and what have you. Due south of the tower, OT, height H, angle of elevation 45. Surveyor then walks 100 metres east, point B, angle of elevation now becomes 30. All right. Express the length OB in terms of H. So if I just redraw that triangle, it turns out to be quite a simple little question. Bit of a gift mark, I guess. So unlike the last one where you pretty much had to do everything, this one's broken into parts where at least you can pick up some marks along the way if you can't do all of it. So OB over H is tan 60, H tan 60. Part 2 of the question then said, we'll show that H is 50 root 2. So using the other triangle, it's a 45-degree triangle, so I know it's isosceles. So I know AO is also H, and I can just use, there we go, bit of Pythagoras. H squared plus 100 squared will be H squared tan squared 60 in the other one. And so we end up with, eventually, playing around with Pythagoras. Oh, still not there. H squared is 100 squared on 2. So H is 100 over root 2. Still not quite what they want. Rationalise the denominator, and we do indeed get 50 root 2. Now they want the bearing of B from the base of the tower. So let's draw that up. There's my compass. O's the base of the tower. Bearing of B. We're out there. We now know that's 50 root 2. We also know AB is 100. So, there you go. That's the angle we want to find in there. Well, obviously it's going to be easier to find the one in the right angle and then subtract that from 180. So AOB, the tan of it, 100 over 50 root 2, 54, 44. So subtracting from 180, we get our bearing of 125.16. 125.16. Some people like to put T after that to indicate true bearing. So you might see that sometime.
Do you have to?
I don't think so. But what you do need to do for a bearing is it needs to be 3 digits. So if you had, say, a bearing of, 62 degrees, you'd write it as 062. And then that would indicate you're talking about a bearing. Yeah. So, okay, 2G, I think, if I remember correctly, is pretty much just using right angle triangle trig. 2H then starts involving cosine rule and sine rule. I think that's how it works anyway.